What would happen if you jumped from space toward Earth? Let's find out. This is the ultimate fall. At first, nothing feels different. There's no air, no sound, just silence. No air means no wind in your ears. You accelerate, but you don't feel it the way you do on Earth. Gravity pulls you down at nearly the same strength as on the surface, but there's nothing to push against. You're in microgravity only because you're falling with everything else. Break from orbit, and you begin a true plunge. Distances are deceptive up here. That blue line is still hundreds of kilometers away. No air, no roar, only your suit fans and your heartbeat. As you fall faster, you hit Earth's atmosphere. Friction builds, and the heat begins. First, the cold. Upper atmosphere near vacuum chills everything. Then compression heating takes over. It's not rubbing friction like sandpaper. Air molecules compress ahead of you, heating to thousands of degrees. Velocity climbs, hundreds, then over 1,000 kilometers per hour, as drag ramps up. Your shape matters. Streamlined posture delays tumble and reduces heating spikes. The air is still too thin to slow you much, but it's hot enough to matter. You'd be moving thousands of kilometers per hour. Without protection, the heat could burn you instantly. Peak heating arrives when the air is dense enough to compress hard, but thin enough that you're still supersonic. Shock waves form. Temperatures can exceed 1,000–2,000 degrees C in the flow just ahead of you. A pressurized suit with thermal protection and cooling is the only buffer between survivable and fatal. Stability is critical. A flat spin could raise G-forces to blackout and structural failure. As drag builds, heating peaks, then declines. You're trading speed for survivability. In real life, astronauts use special suits, like the famous space jump by Felix Baumgartner, to survive extreme speeds. He leapt from the stratosphere, not orbit, but still broke the sound barrier on the way down. Even there, spin management, suit pressurization, and oxygen systems were life or death. From orbit, you're at roughly 28,000 km/h. A vertical jump from high altitude starts much slower, but both face extreme conditions. Drogue chutes stabilize first. Main canopy opens only when the air is thick and your speed is safe enough. Planning, weather windows, redundant systems. This is engineered survival, not a dare. With the right gear, you could slow down and safely land on Earth. Drogue reduces speed and stabilizes your fall, aligning you for main chute deployment. Now the canopy opens. A staged reefing system prevents a violent jerk that could damage gear, or you. Descent slows from hundreds to a few meters per second. You steer, scan landing options, and breathe again. Below, recovery crews track your path, ready to assist within minutes of touchdown. A controlled flare, knees together, roll with it, and you're home. But without protection, the fall wouldn't end well. Vacuum causes embolism. Fluids boil at body temperature. Then heating, hypoxia, and unconsciousness within seconds. A flat spin could impose lethal G-loads. Thermal and mechanical stress finish what the vacuum started. Space is not forgiving. Space is beautiful, but unforgiving. Every safe return is a triumph of physics, preparation, and respect for the void. Subscribe for more mind-blowing space facts. Stay curious.